Now we are not going to discuss the steady state condition, rather we are going to discuss the transient case. Before I discuss transient, let me discuss a few things that what do you expect in case of a transient operation, how your reactances should behave, your what would happen to your armature reaction, whether it will increase or whether it will decrease. The thing is that first let me give you a prelude regarding that. Suppose what is a transient? Suppose in case of a AC machine, say your rotor part supply is remain same. Here we will only consider whatever transient will come or whatever disturbance will come only come to our stator side circuit. Let us consider that rotor circuits are remaining means remain same. They are still intact. Whatever winding we were having, like uh, D axis, F winding means field winding, and KD winding, they remain same, as well as Q axis, G winding, and Q winding. They are also remain means in their means remain in operation. However, in A, B, C phase, it may so happen that fuse of phase B may blown off, or it may so happen that there is a, even in case of a normal condition also, when it's not unbalanced, even in case of a balanced load. First, let us consider that there is a sudden load increment. Suppose somebody just switch on his means some additional loads are connected to our machine. Then what will happen to the machine, right? Means how the means the trans what will happen to our armature reaction. Now we are means habituated to do the steady state analysis, but think about it. Suppose when you are suddenly increasing your means electrical load, then what will happen? The means even if your machine is so designed to means maintain constant operating condition, we will let us consider the electrical transient part. Mechanical transient part we will consider later. In that case, what will happen? Like your reactances, or let me tell it in terms of flux linkage. So suddenly that flux linkage, your field flux linkage suddenly cannot change, but your armature flux linkage, because armature number of turns are comparatively less than that of field winding turns, and armature current is you have introduced that change in armature current. So there will be a huge, means a considerable change, a tangible change in your armature current, and that is suddenly going to change your flux linkage of armature winding. Now we must investigate that how this change will affect our DQ0 model, right? And we'll try to find out the nature of our system model during transient and also subtransient condition. What is subtransient? Means just after introduction of your disturbance, whatever we will observe, that is the case of subtransient. And after means few second, means not few second, few millisecond, will observe the subtransient condition, and gradually that from first few milliseconds we will observe subtransient, and after that we will observe transient, and once transient state is over, the machine will enter in the steady state condition. The duration of subtransient and transient you will learn in detail in power system, but we must know what is subtransient and what is transient. So see here that equation, like our this one. First, consider about damper winding. So, in case of a damper winding, what do you think? That in case of a damper winding, the damper winding uh, resistance should be high or low? Means we should design the damper winding with a very high value of resistance or with a very small value of resistance. The obvious answer is that we must design the damper winding resistance with very small value. Why? Because if we increase the damper winding resistance, then what will happen? The We should design it with a high value of resistance. Why? Say, consider or forget about means considering any physical system. Then it will consider a three-phase induction motor. So, if you want to increase the starting torque, right? When the slip value is comparatively high, then or what you need, you need a very high value of rotor resistance. So if you consider, then you will see that damper winding conductors are nothing but there's a rotor of an induction motor. So if we increase the resistance present in the damper winding, then what we can do, it can damp down that means oscillation, or uh, it will exhibit a tendency to generate more damping torque towards suppression of any kind of undesirable oscillation, whether it's acceleration or retardation. Therefore, if we now another thing, that when you are having a damper winding, then what will happen? Suppose, let me tell you one case, two circuit you consider. One is one means resistive bulb, tungsten filament lamp, and another one is not this electronic choke, but previous uh, means old fluorescent lamp, means old uh, fluorescent lamp means with conventional ballast, that is having only a high value of L and a starter to control it. So here, if you have in your house or in anywhere, you see that this means bulb, this resistive bulb, once you switch on, it will it will develop or it will give you the full lumen output, and also current through it. If you can measure it by any measuring instrument, any suitable measuring instrument, you will find that the current instantaneously change to its full value. It never undergoes any sort of oscillation or any sort of transient. But in case of a fluorescent lamp, when we switch it on, at first the current undergoes some kind of transient state, and then finally the current reaches its steady state condition, and also the fluorescent lamp gives us the full lumen output. So the damper winding due to so in a nutshell, what we can see, uh, if we compare the two circuit, that one bulb that is purely resistive, another one that is RL circuit with high value of L, like your fluorescent lamp. What we will observe that in case of fluorescent lamp, it's means this current first undergoes a transient state and then it reaches steady state. Now, with this analogy, if we come to our damper winding case, as I have mentioned, that damper winding resistance is comparatively very high than that of normal synchronous machine winding resistance. That is why damper winding current damps down at a very fast rate. Even if you have difficulty in this, consider a RL series circuit, LDIDT plus RI. Let me write here like L DIDT plus RI. This is the circuit equation, and the circuit description is like this, like you are having simple R, a simple RL circuit. So for this you will have what? You will have L di dt plus Ri. Now, when you will solve this equation is equal to, say, if you apply a voltage V, you will see you will get a current value like, say, if it is a VDC, if you apply, then you will see the current I, you will have an expression I is equal to sorry, just a minute. I is equal to, actually there are lots of scratch on my screen, so I cannot write it very clearly, by R 1 minus e to the power minus t by tau, and this tau is equal to L by R. So what we can see here, this tau, if we increase this L by R, so you can understand the nature of the current here in this circuit. It will be monotonically increasing function like this. If this is your time, then you will have a current like this. So if you increase this tau, then what you will have, your machine means, or your system, this depends on your tau. Typically if it is 98%, then it is 4 tau. So if you increase tau, then the system will take more time to reach steady state. In other way, what we can say, sorry, winding with high R, winding with high R, transient is period transient period is very short, right? So if winding resistance is very high, transient period is very short, right? So here you can see now, hello. So now here one thing it's very important to note, that we can see that E power means resistance value is high, then transient period is short. Therefore, damper winding undergoes a very short transient period, but rather the other winding. Therefore, we can consider that the damper winding current IKD and IKQ, this delta, this delta indicates this delta indicate the change. This delta indicate the change. So here delta I kd double dash and delta I kq double dash indicates the change in damper winding current. Now in case of transient period, we are also considering that our machine flux linkage, that is a lambda f double dot, that is also dash, that is also constant. Why this lambda f uh, it is constant? Because we are assuming this. Now let us quickly revisit the equation of lambda f double dash. Here it is the equation of lambda f double dash. You can see, okay. Now if we assume that our these values are constant, means these inductance values are constant, then we can write del lambda ff dash is equal to lmd del id plus lmd del ikd double dash plus lmd del iff double dash. Due to space crisis, I can write only one term. You can understand. Now, here you can see that as we already know that del ikd term is 0. So that gives us this term is equal to 0. And from this, what we can write, actually our objective is to express uh, if del if in terms of del id, because del if is a stator del if is a rotor current. So you can write okay, one there is a small mistake I have made. It should be del if double dash, means refer to stator. So from this we can write del if double dash. From this equation I am writing del if double dash is equal to minus lmd by lff dash del id, right? Now if we replace this del if double dash with this expression in our second equation of del lambda d, then we'll get this expression for our del lambda d, right? Now if we define our transient response, then we'll see that LDTR, sorry, that video got it was interrupted due to some unprecedented unprecedented error. So let me tell you one thing here, that I made a mistake. It was not transient response, rather it is transient inductance. We call this LDTR as this one as transient inductance. Right, this transient inductance we are defining, this one is our this lambda d, this is our flux linkage, or rather it is not lambda d, rather it is del lambda d, means this we are defining like change in flux linkage, means change in flux linkage, this one. And the second term, this delta id, is a change in current, means here basically we are writing that it is and if we do this simplification, sorry, we are getting this result that ld is equal to minus lmd square lf double dash. So obviously you can understand this lf double dash. If you see the expression of lf double dash, it is field inductance, and you can expect that lf double dash would be, it is a number of turn is more, so you can expect lf double dash is not a small number. But uh, anyway, the numerator is also a square term of an inductor, and the whole thing you are subtracting from LD. So what we can conclude in nutshell, that this LDTR is sorry is less than LD, we can write LDSS, that is the steady state value, that is equal to just LD, right? It's less than that. And following the similar analysis, we can find out it for LQTR, that is the transient reactance along Q axis. So with this, let us see what kind of equivalent circuit model we can get, or what is the voltage behind this inductance, right? So before I discuss this model, let us analyze the voltage behind the inductance. Like this equation, that this one indicates a relation between our del lambda d with means change in del lambda d means let me highlight the equation first. This equation I'm talking about, it indicates what? It indicates the change of del lambda d with del id. So this del lambda d and del id, it is means establish one relationship. And here we are assuming that both id means the direct axis current and if or if double dash, the field current through direct axis winding, are free to change. Now similarly we can have a similar kind of relationship, like we can have means del lambda q is equal to LQ minus not that sorry, let me write, it should be like this equation. It will be del lambda q is equal to LQ minus here it would be LG double dash, right, del IQ, sorry. The problem with smartphone is that they always not behave like a smart creature, and sometimes they behave terribly unsmart. Anyway, sorry. So this we can do now with this expression. We'll get lambda dtr and lambda qtr. So this lambda dtr and lambda qtr, further we can write that our means lambda dtr, we are mentioning this as we are trying to view this lambda dtr, this one lambda dtr, like lambda dss minus delta lambda d, right? Lambda dtr, this first lambda d indicate it is like our steady state lambda d, like lambda dtr is equal to lambda dss minus del lambda d. Now here we know how del lambda d depends on ID, right? So we know how del lambda d is dependent on our ID. So with this, sorry, uh, now let us once again identify the components in lambda d and lambda q, which will remain unchanged by a transient stator current under the transient condition where both lambda f, means the field along direct axis and field along our q axis winding, are held constant by changes in means if dash and ig dash. What I'm trying to say here, it's the very basic thing that uh, uh, okay, like uh, we are claiming here, please pay your attention that lambda f and lambda g, these two are constant. Now if these two are constant, then what does it imply? That if lambda f and lambda g are constant, does it imply that if and ig must be constant? Actually no, because if we see the equation here, from here you can see that lambda f dash, it depends on your id and if. Now what we are claiming this, first of all we have already said that this one is 0, but this two term remains, and we can always keep this delta lambda f double dash or delta lambda f is equal to 0 by means making a proportionate but means opposite change in the two term, like uh, if this LMDID, if it is increased by plus 5, then we should reduce the field current, so this term should decrease by 5. So total plus 5 minus 5, your delta lambda f double dash will remain same. Now if that is the case, then what we'll be getting here, this one, this will get that delta lambda d, right, is equal to this lambda d minus LDTR ID. Now similar definition we can get for lambda q transient, that is the transient value of our direct and quadrature axis flux linkage. Now let us consider the definition of speed voltage terms that is associated with our lambda q d, means lambda the transient value. The speed voltage terms that are associated with this, if we see the model, that model we initially consider, this lambda d PQR and lambda, sorry, this one is lambda D PQR and this one is lambda Q. These two terms, this lambda D P theta and lambda Q P theta. I'm repeatedly telling or getting is making a is mistakenly pronounce it like it is QR. It is not QR. It is lambda D P theta and lambda Q P theta. Now, in transient case, what will happen? This lambda D P theta will become lambda D TR, and P theta you can write omega R also. This. And similarly, this one will become, the second term will become lambda QTR and multiplied by omega R. Now, if this is the case, then see, here we can get one thing, that is that the speed voltage associated with q axis, we can write it is EQTR, is defined as omega r into lambda dtr. Then omega r, from the definition of lambda dtr, we are getting this expression. And then if we perform some sort of simplifying analysis, we'll get this overall expression, right, that we are writing over here. And finally, the same equation you can derive for direct axis, only the sign will be reversed, as we know that these two are having different sign. So this EDTR and UQTR, we can consider they are the voltage behind transient. Now this is our D-axis circuit model. We can do it for Q-axis also. Like here, as we can see, this equivalent D circuit condition during the transient state. One thing here I just forgot to mention, that this it depends on your means lambda f double dash, means now if lambda f double dash, if you have considered that lambda f double dash remain unchanged, right? So this will give you a voltage value. So this is our voltage behind the inductance, and we are getting a model like this. Like here you can see, this is the model. What is the difference here? The IKD, as we have already mentioned, that the damper winding resistance is much more greater than the other winding resistance. Therefore, we will still consider that damper winding current is zero, just like our steady state condition. But there is a change. And what is that change? That unlike the previous one, like if we go to that model, the normal D-axis model, here you will have this omega lambda q. But now you can see that this omega lambda q is not there. Why? Any guess, anything comes in your mind that where means it is okay, this is equivalent L, fine, But why we are not showing the means where does it disappear, this omega dtr, or can we just discard it like that? Any guess? Okay, so or in case of this inductance model, just because it is an inductance model we can neglect the term, but in that case also we are showing this vf and ikd, but why we are not showing that means speed emf here? Or means if we consider this as a model, then where you are going to apply this feed EMF, where it will appear, whether it will appear across these terminals or somewhere else, that we have to determine, right? Now this is all about the transient. In our next video we'll learn about sub transient, and then it will be over, right? Start with the last part, that is the sub-transient inductance, that is that takes place at the very beginning of your means operational period. uh, it's just after a few milliseconds of your switching instant. So in case of sub-transient period, transient current that is induced in your rotor windings will keep the flux linkage of every rotor circuit initially constant, means means transient currents whatever it will be there, the flux linkage of rotor circuits will consider it remains constant. However, that is not the case with the stator circuit. So our virtual winding, that is means we are referring our means main winding ABC to a virtual winding QD0, and that is rotating at a certain speed. With the d-axis rotor, flux linkage held constant, and that is how we are getting here delta lambda f double dash is equal to means I'm talking about d axis. You can similarly do the similar kind of analysis for q axis also, is equal to 0. Now here you can see this delta lambda f double dash. From our expression we can write its equation. Now in case of previous analysis, we were considering this term to be 0, this one, the last term during transient period, uh, uh, transient state, this means IKD or delta IKD all were 0. But here in case of subtransient, we will consider that is the very beginning of our operational time. The although the resistance present in our damper winding is very high in comparison with the other windings, but still it is not able to completely means, uh, means decay or damp the initial transient. It is bound to happen that damper winding current is also bound to undergo certain kind of transformation. So from these two expressions, what we will write, and also see the difference with our case of transient analysis. In case of transient analysis, we consider this. Okay. Now, in case of from these two, now the main difference is that previously delta I kd double dash means, let me write it, otherwise it will become difficult for you to understand. or del I kd double dash is equal to 0. But in case of subtransient, this that is the main difference. So here we will from these two equation, what we can do, we can solve for means solve means we'll try to express these two current. See here there are three currents are there. One is delta id, that is our stator current, and another two term, this delta if double dash and these two are rotor current, right? So our objective is to express everything in terms of stator. Why? Because the stator is our means the, we can say, the input port or output port that is accessible to the outside world. So here we'll try to explain or express everything in terms of delta ID. So once we express it in terms of delta ID, we got this expression, right? And once we have this expression, the corresponding value of flux linkage we can write accordingly. That is delta lambda d. And from this delta lambda d, like previous case, we were finding out some we are finding out L D T R, like delta lambda d by delta id. Similarly, here also we'll try to find out the same thing, but as the time is very short, here we'll define it. And the main difference between these two circuits is that in case of your previous case, your damper winding current was 0, and now it cannot be equal to 0, or the rate of change of current is having some finite value. So here we proceed. These are all mathematical manipulation. We'll be able to see or establish that LDTR, if you see this LDTR, and if you compare its rather LDSTR, this STR, this indicate it is a subtransient state inductance. So this LDSTR, if you see magnitude wise, what was your LD? Let me write down the expression of LD. LD was, LDTR. LDTR was like LD minus LMD square by LLF double dash, right? This was our expression for LDTR. Now here, in case of our this subtransient case, we are observing this LDSTR is only LLS plus all these terms. Now, what is the difference between L? For your ready reference, let me write down the expression of LD also. That LD is equal to what? LD is equal to LLS plus LMD. right? Now with this expression of LD, previously we are having LD star here, like this LD star we are having this LD, sorry, LDTR, not LD star, LDTR. This LDTR was this LD minus LM square TF double dash, right? And the another thing here, sorry, here this means LD star means LD subtransient, that is means the expression clearly reveals it is smaller than LDTR, right? Now let us see how the equivalent model we are getting here. Now this LDSTR, here let us see this LDSTR, like previous case we can write LD minus delta means lambda d minus delta lambda d, and this time it is like here I have made a mistake, a small correction please. It is not LD double dash, rather this term, it is not correct. You please replace this with this one, LD star ID. Similarly, the second term, this LQ dash is not correct. Please replace with one thing I would like to mention here, that I want to ask that previously we used to consider delta ID while finding out this LDTR delta ID, but while we are using it in later on in derivation, we are writing it like LDTR ID, means here it should be, means this expression it should be LDTR delta ID, but because it is delta lambda d, but we are writing LDTR ID only, not delta ID. Why? That we have to figure out. I hope I make sense. This delta lambda t, previously it was delta lambda d by delta ID, but right now we are writing it like LDTR into ID. Why? What is the logic behind this? And if you want to answer this question, want to find out answer for this question, I would like to tell you that this delta ID is never is equal to right. Del ID means a small incremental change in, small, very small change in the ID. But this DIDDT is means you are measuring the rate of change of your ID with respect to rate of change of your current. So one thing here I would like to once again mention that if you see the unit of delta ID, then it is still in ampere. But if you take DID dt, then its unit must be ampere per second, right? So keep it in your mind. That means this we can, at least dimension wise, we don't have any problem if we replace delta id by id. But in the later analysis, we are replacing delta id by id. Why? That is the main question. Then in the previous case, why should we use this delta id? And similarly, here also we are using this while defining the L T star. We are using delta id to find it out, like here in this derivation. But later on, you will see that here we are not using delta d tr. There is a circuit mistakenly entered here. Actually, it was showing that the speed means speed EMF, uh, that is the voltage behind our transient. So basically, if you solve it, you will get an equation like this, where your ED subtransient is totally dependent on your Q axis variable, and your equivalently you will have for Q, you will have it's dependent on dx. Now transient time constant we can measure, but that is not under the purview of current discussion. Here we, our objective was just to see that how this transformation is helping us to remove all the rotor position dependent term. And the second issue was that how we can handle or deal with the transient model. And of course, I have also explained that how this, if we transform it, then how we can only, means it is like zooming a particular part. Means if you transform, I have already delivered a lecture on transient, so you can understand this. Now see the last and interesting thing, that the LD STR, it is not LD double dash, rather you should read it like LD STR, right? This LD STR model, when we are considering transient model, in case of transient model, you will see that this transient model, it was a current source. Why current source? Because we know that this IKD double dash is not going to vary, because it is the transient period. Already that during subtransient period, whatever oscillation was there, it is over. So we can assume that the voltage, the current flowing through our damper winding will remain constant. And as it is remaining constant during the entire transient state, this means considering this with a current source is a valid approximation. But when we are considering the subtransient state, at that time we do not know that the current will remain constant. Rather, what we know, that being a short circuit, the voltage across that winding will be zero. So that is why we are replacing that current source by a voltage source. But when you will try to find out the Thevenin equivalent of this, means the way we are looking at this circuit, we are basically trying to figure out the Thevenin equivalent. Then you will see the Thevenin equivalent, how you should replace this current source, this voltage source, all this must be short circuited, right? So if you short circuit them, then what you will get here, your total inductance will become LLS plus a parallel combination of LMD, LF double dash, again a parallel combination with LKD double dash, right? Let me write it once again clearly. From this circuit we can write not LD double dash. This is in series, and the other two, these will come here, and also these will come here in parallel. So we'll get in parallel with LF double dash in parallel with LKD double dash, right? So this will be our equivalent circuit, and if we check it, the expression, you can see we got the same expression here. It is just like a parallel combination of parallel circuit. First you obtain parallel combination of LKD, LKF like this two, and then you obtain the parallel combination of this. So I hope you understand the subtransient model, and also it is very clear that in case of subtransient model, uh, in case of in this context I would like to mention here, in case of transient model, when you want to obtain, then what you will have here, you will have LS plus a parallel combination of LMD in parallel with LF dash. Oh, right. You will have LDTR is equal to LLS plus LMD parallel LLF double dash, right? So this is the parallel combination we'll have here, and this branch, as the current source is 0, when you are look for a means equivalent circuit, this LKD double dash won't have any effect. That is why the in a single line we can conclude that two things we can conclude here. One, that LD STR is less than, that is very obvious because we know inductance and resistance, they follow the similar property. If we keep means add more resistance in parallel, the effective value offered by the parallel combination is less than the individual resistance. So same thing is true for inductance. So it is obvious that LDSTR is less than LDTR. And another thing that is also very important, point number 2, that is in case of LD LDTR, in case of LDTR, LLKD double dash has no effect. However, in case of LDSTR, LDSTR by virtue of its connection is less than LLS plus LKD double dash. Now you may ask that why I am writing this, because if you see the combination of these three inductance, this MD, that is the mutual inductance, obviously this should be having a very high value, otherwise power transfer is not that easy. And LF dash, that is the field winding inductance, it must be also have value. And this LLKD, that is damper winding inductance, and as I have mentioned that damper winding is a mainly a resistive winding with small value of inductance. It is not desirable that. So the issue here is that your LD double dash become less than LLS plus your uh, LKD double dash, right? So I hope you understand this transient and subtransient period.